The presentation that Gervais gave before is very interesting because he mentioned a very important thing, which is you should be maintaining more than one environment. You have your production, but you should definitely have your staging and your pre-production and some 20 environments and who knows what. I work for Arrikto. Arrikto does storage mostly geared towards Kubernetes. The classical question is, how many of you use Kubernetes? Can I have a show of hands? Lots of people. How many of you use Kubernetes for the stateful part? Not just for the stateless, something can go down and then come back up again and everybody's happy part of your applications. Not many people. Why? Because it's difficult. What's the difficult thing about it? Persisting data, right? And recovering nodes. And then everybody needs a multi-cloud strategy. How many of you are actually looking for a multi-cloud strategy or have been asked to contribute to a multi-cloud strategy, whatever that means? So what do we believe is a multi-cloud strategy? And why do people need to work across multiple clouds? Reasons of cost efficiency, reasons of applications that are only available in a specific cloud. So I want to do AI or Google's new offerings or whatever. So I've got many environments, I've got many users that have distinct responsibilities. I've got the people that run the ops part and the people that do development, and yes, everybody does DevOps, but there is developers and there is people that actually run production, right? So they kind of have different goals and different responsibilities and different things that make them click. That was a pretty generic introduction. Okay, what is it that we do? And what's the important part that I should have pointed out? The important part about having multiple environments is data. Someone has to produce this magic piece of test data. Who does? Who knows? How efficient is this data? How well does this data actually capture the state of production? Who knows? What happens if this test data doesn't actually capture the state of production well? Bugs, that's what happens. When do these bugs get discovered? In production. Because that's where the data is that causes these bugs to appear. This is kind of logical. Okay. So, this is the general things that we can talk about afterwards because it's a 20-minute presentation and I can't fit all of these things in 20 minutes. But the general idea is, how do I run stateful applications on Kubernetes? I run them over some sort of persistent storage, and Kubernetes has abstractions, for example, stateful sets, to help me run my stateful application. What's my stateful application? A database, for example, Cassandra, an HDFS cluster, a MongoDB installation. Can I use local ephemeral SSDs, NVMe to do that? No, I can't most of the time because if a node goes down, I'm in big trouble. Can I collaborate at global scale? And what does collaboration mean? How cool would it be? People talk about infrastructure as code, as in infrastructure, as immutable code, as commits. Okay, so if I've actually implemented the DevOps way of doing things, why can't developers take the definitions of production, apply them to their own infrastructure, which is completely distinct from production, different users, different accounts, different credentials, even a different cloud, and have their own production clone, so they can work on it. Can they do that? They could. What it is that they're missing? The actual production data. What is it that we do? We give you a way to snapshot the whole application and refer to the whole application along with its data as a specific data commit. That's what we do. So if you want to recreate production, as in recreating production as it actually is, as in not losing data, we can do that. Why is it important? Because then your developers can do that, your analysts can do that, other lines of business can do that, and they can actually have something that's meaningful and real and close to reality. So this should accelerate DevOps. That's our main premise. How does Kubernetes help? Kubernetes brings an immutable, declarative, version-controlled way of referring to what you want your infrastructure to do, to how do you describe your application, essentially. So, The way we see things is, yes, people are moving and will move faster towards running their own persistence layer on Kubernetes. We can talk more about it afterwards. We've got quite a few reasons why people should do that, and people are realizing it more and more. It's just difficult to do. Kubernetes operators help, for example, in this regard. Okay, and then use our software to be able to snapshot and recreate the whole stack. We work alongside Kubernetes to snapshot everything and be able to recreate it. Why is this important? Because you can then actually create transformation pipelines of this data. Because when someone hears, yeah, I'm going to snapshot my production and give it to my developers, they're like, yeah, but my production has PII and maybe my developers should be able to see everybody's SSN. I get it. How should I handle it? Should I have a person actually going through all the callings and deciding what calling to mask and what calling to read? No. The transformation itself should be something that I declare on Kubernetes, should be a blessed image, an application-specific blessed image. And changing this image goes through all the DevOps pipeline. How do you do that? You do it if you have a way to referencing your data along with your images. That's what we enable. We can't do the anonymization ourselves because we are a storage layer underneath the application. Please feel free to interrupt if there's something that you disagree with or if there's something like that. Okay. And then you can actually sync and share what you've created with other people you don't necessarily share access credentials with. Because you can't have how many of you actually do development? And sometimes just these ones had to log into production so you could see logs, or you could see the bug actually happening. No developer ever logs into production, right? Of course, developers log into production because that's where the data happen, the bugs happen. Okay, and then as an added bonus, if you do something like that, maybe you don't need shared, expensive, slow, external storage. That's our main thing. So this is what we do, and this is what I'm going to be demoing. Left-hand side is your on-prem, let's assume, production. And this is an actual stateful application, let's say 3 Cassandra nodes that run in 3 pods on Kubernetes. We can snapshot it, as in thinly snapshot it incrementally. We get the snapshots, split them in chunks, make them immutable. We can synchronize them to other clouds. So this could be Amazon or Google, wherever it's cheaper for you. Or because that's a transformation point, you may want to run it in your on-prem infrastructure so that your data doesn't escape your data center, okay? So we can clone this into a distinct copy. Then you can transform it, anonymize it, convert it, whatever you want to do with it. And then we can produce new snapshots. These snapshots are now anonymized. They're ready to share with not so trusted people. So you can move them to your cloud. Why? Because that's where you can run your inexpensive AI models using GPU-based VMs. So someone clones it. They have their own stack. Every single engineer has their own stack, a thin clone. They run their test cases. You want to change your database schema? Fine. Snapshot your production database, clone it somewhere else, destroy it, or just do everything perfect the very first time to try anything out, and then go back to production and do what you discovered and what you learned. That's it. So this is what I'm going to be demoing. So, my windows are a bit messed up, but we'll fix them. Left-hand side is A. A is your production. Rock is our software. Rock is our data services layer that runs inside your data center. It's our persistence layer. Okay? So that's A, that's B. Rock has buckets. Buckets contain snapshots, full applications. So that's an older bucket that I used. Inside this bucket, there is Kubernetes Cassandra. That's a snapshot of a whole application. This snapshot actually has 3 sub-snapshots. Why does this application snapshot have 3 sub-snapshots because Cassandra runs on 3 nodes. And this is a group-consistent snapshot of Cassandra. Okay, I can actually go into this snapshot and see that it's versioned. There is a single version, but you could see here multiple point-in-time snapshots immutable of your application. So you can refer to your application as D86DA. That's your application at that specific point in time. You can roll back to it, you can give it someone else, you can transform it, produce new snapshots. That's it. Okay. How do application snapshots go from A to B? And A doesn't actually trust B. Okay. So this bucket is published. Published where? Published to a registry service, which is similar to GitHub. So rock is to Git, what the registry is to GitHub. No data actually crosses the registry though. The data flow directly from A to B, or from A to multiple points, and the registry keeps track of who is interested on what data, and the registry is the point where you specify policy, where you set access control lists. There's a central point where you set access control lists, and then this policy is enforced in a decentralized way. So let me log into the registry. The registry has buckets. These are buckets. Buckets have links. So some sites publish buckets, creating the links. Some other sites subscribe to buckets. You don't just have to have the link to subscribe to a bucket. You have to prove yourself to the registry. You have to prove that you're a user that's part of a specific access control list. So that's what we're going to show now. Are we in sync so far? Yes, no? Please ask questions. Okay.
Regarding the buckets.
Yes.
So what is kept? What state is kept there? Like say Cassandra. Is it?
We keep snapshots of Cassandra's persistent volume. We maintain Cassandra's disks, the full PV.
Not Docker images like with the application code or Kubernetes description.
So here's the fun part. You can use this for Docker images as well, but this example maintains Cassandra's PVs only. But what we also maintain is the full metadata for the application. So if you go here, you will see that this version has metadata, and the full YAML description is part of this snapshot. It doesn't show nicely because it's a big blob of text, and here it's just online, but we maintain the full YAML metadata. So we maintain the image references. So if your image registry exposes these immutable images to your other site, you can recreate your application. Everybody has been doing this with images, and everybody does image transformations and image pipelines. We give you a way to do it with your actual data. Make sense? Okay. So let me create a new bucket. Let's call it DAX SFO1. It's going to be a published bucket. I'm going to be publishing it. I'm going to be publishing it to this organization, that's our organization, on the registry. Okay? It's going to be a private bucket. Only members of this organization will be able to access it. Okay? Why will the registry trust this rock deployment? It doesn't. So I will be redirected to the registry. I have to log into the registry to essentially authorize this rock instance to publish to this registry bucket. That's how we enforce policy. So I'm being redirected to the registry, and the registry asks me, are you sure you want to allow this data center, this rock instance, to access this bucket? Yes, I allow it. And from this point on, this rock instance has tokens to be able to publish data to this bucket. So this bucket is published. It's an empty, published bucket. This bucket has no peers. Nobody else is interested on this bucket. Only this single rock deployment is interested in this bucket. Okay? As a matter of fact, I forgot to mention, A is an availability zone on Amazon, B is another availability zone on Amazon, but that's just an implementation detail. A could be Google, B could be on-prem. But this specific example runs on two distinct availability zones on Amazon. Okay, US West 1A, US West 1B. So let me go to B now. This is B. Does A trust B? No. Does the user on A, is the user on A the same as the user on B? No. Okay, but they happen to use the same username because it's actually me. Okay. So I'm logged into B. Let me go to the registry. This is my bucket on the registry. I copy the bucket's link. I go to B, create a new bucket. I'm gonna call it subscribed docs SFO. It's gonna be a subscribed bucket. I provide the link to rock. Will the registry trust this rock instance? No. So I have to be redirected again. This is a one-time thing. I'm establishing policy initially, and then by choosing what bucket to place my snapshots in, I make this policy work. Okay, so again, I'm redirected to the registry. I'm actually logged into the registry. That's why the registry doesn't ask for my login credentials at this point. Do I allow rock B to access this bucket? Yes, I do. So B has a subscribed bucket, and our tokens expire after 1 hour. Okay, so this bucket has one more peer. This is B, and its peer is disconnected. It will refresh, and it will be A. This bucket has a peer. This is A. Its peer is B. This bucket's here peer is A. This bucket belongs to B. So a connection has been established. Data will flow A to B, or it could be A to B to C, or any other combination, now that they've proven themselves to each other. Okay, now what? This is our empty bucket. So pay attention to B while I'm doing things on A. What is it that I'm going to be doing on A? Snapshotting the application. What will happen on B? The snapshot will appear. That's it. So I'm now on A. I'll be bringing information inside Rock. Rock is integrated with quite a lot of platforms. It works alongside VMware, OpenStack, Amazon Cloud, Oracle Cloud, VMware Workstation on your laptop, Kubernetes. This specific deployment is tied to Kubernetes. So it offers to snapshot stateful sets. Stateful set is the abstraction that Kubernetes uses to handle stateful applications. So I give it the information it needs to actually prove itself to Kubernetes. It auto-detects namespaces and everything. And here's a stateful set. Here's our Cassandra. Okay. How will you be sure that I'm actually snapshotting a Cassandra right now? So to prove it, I'll switch to this nice command line here. Let me zoom in a bit. This is actually Kubernetes on A. This is Cassandra running on this Kubernetes. I'll get this IP. I'll do a small write. I'll write a few things, and then we'll see them on the other end. This is its IP. Okay. I have my very helpful cheat sheet here because I can't remember this stress write command by heart. So I'll be writing a few rows in Cassandra. Now, let's choose a random name for the key space to make sure we've snapshotted the right thing. Can someone give me a number, for example? Any number?
42.
42, we'll use 42. So I'm writing data into key space 42. Okay, I'm on 1 right now, right? US West A1A. I'm on A. Okay. So I'm writing to this Cassandra. This is a whole stateful application, by the way, right? The full stack. We're using a simple example now, but it could be the full stack. Okay, I'm writing, I'm done. Okay, I can actually go and repair this Cassandra. That's a very expensive operation in Cassandra to make sure that all 3 nodes have the exact same set of data. So I can find that it's repaired in the clone as well to prove that it maintains all state. That's just a Cassandra operation. We don't do anything rock specific here. Okay, so Cassandra makes sure that all nodes have the same set of data. Okay, and obviously 1 is also repaired, and 2 is also repaired. So my cluster contains data, and it's in a consistent state. Okay. Back to rock. I'll be snapshotting this Cassandra cluster. That's it. I start the operation. This happens asynchronously as a new task. What happens is rock at this point snapshots all 3 pods on Kubernetes as a group consistent snapshot. When this is done, this takes about a minute for this example. We can talk more about how we do it at the lower level. We have quite a few storage drivers there to do that. When this is done, you'll see that the snapshot appears here. Why? Because I'm snapshotting something in a bucket that's published to where this bucket is subscribed. This will be a concrete snapshot. This will be a pending snapshot. Why? Because we need to allow for some time for the synchronization to complete. When this is concrete, we'll clone it and we'll find our data. That's it. So what happens underneath is rock snapshots each pod. The pods are actually local. These pods work over local SSDs. So Cassandra is as fast and our storage is as cheap as possible. And then the snapshot appears here. So this is done. And the moment it happened, you first show 3 sub-snapshots appearing, and then you show them being assembled into a group. So this is now synchronizing, and you can see the moving dots over there. And we can go see if we actually make it. It's now at 100%. We missed it. It was synchronizing at about 180 megabytes a second, which is very good. And this is over a single one connection. So we have our Cassandra here. Now what do? We will present it, clone it into a new resource. So B happens to be connected to a Kubernetes cluster. It could be VMware, and we would be presenting 3 VMware VMs. You can see the full application definition here. I'm providing the tokens. This is the only difference. We annotate the application definition, so it points to a specific data commit. We say, I want this application to be seeded based on this snapshot. That's why we'll find our data there. Okay, I'm presenting it. Again, a new asynchronous task. Now, this is B. B was originally empty. What's going on B? B has pods. Cassandra, let me get it full screen. Cassandra 0 is being created. Then Cassandra 1 will be created. Then Cassandra 2 will be created. That's standard Kubernetes, by the way. This is Kubernetes spawning our Cassandra. And then we'll run a stress read, find our data. Our demo worked. We're out of time. That's it.
individual pods?
As you saw, we can see the YAML file afterwards. The YAML file specifies a stateful set. So these pods are being created as part of a stateful set, and there's a very specific section inside the YAML that says volume claim template, where we provide templates for each individual pod, and this is where we said, I want 1 terabyte disk for each pod, and I want the whole template to be based on this snapshot. Make sense? Any other questions so we can overlap with, yes?
General question on multi-clouds. Today you can spin up a cluster of VMs or container easily on multiple clouds and on-prem. What if your data set is large, say multiple terabytes? Where do you keep it? How do you move it between clouds?
Okay.
Or do you move mobile copies?
Okay, so spawning a single cluster across locations, we don't see that as multi-cloud because it's still a single deployment, a single cluster. It just happens to be spread across two locations.
No, I can spin up multiple Kubernetes cluster on Azure, Google, and AWS, and on my VMware cluster.
You're saying that you can spin multiple Kubernetes clusters, one on Amazon, one on Microsoft?
Using Terraform, you could easily.
Of course. What happens to your data? That's the question.
Exactly. What do you do with data? We got terabytes of data.
So we are on the side of the persistent volumes. We can snapshot them. We do this incrementally, and we store these snapshots on inexpensive objects on an inexpensive object store. We store them on S3 if you're on Amazon.
Sure.
So the very first time you snapshot your full terabytes, it's going to take some time, right? But afterwards, we only need to extract the differences, and we update these snapshots. So we have multiple point-in-time snapshots, and they share part of their data. You don't have to copy all these tens of terabytes into S3 again. So you can actually use us to protect continuously your whole stateful cluster with multiple points in time. Make sense? How much is your cluster? 20 nodes, 2 terabytes each. Is that a good ballpark number?
So you want to operate on the same data set on multiple clouds. How do you access your data set?
We operate on distinct snapshots of the same data set. If you want to have multiple people actually accessing the same production database simultaneously, then that's what you should do, but then you're in trouble. Our premise is that people want to see different views of the same data, different clones of the same data, because this is actually what they're doing with images. Nobody's actually working inside the same branch at the same time. They branch and then they reconcile. You produce an image, I can refer to it, I can get it, produce a new image. I'm not modifying your image. Everything is immutable. Then someone maintains properties that point to the right data sets. That's our premise, right? Other questions? So this is done. And just to prove that, we had actually snapshotted data 42, it's going to take like 2 minutes. Back to the cheat sheet. Where's the read commands? This one. So pod IP is now this one. Okay, I'm doing a read. I have to provide the name of the key space, otherwise this is going to fail. 42. Okay. And there's going to be a single exception because the stress tool actually tries to contact the old cluster. The old cluster is not available because it's a completely distinct deployment. And then you see that it reads the rows I wrote before. So this is actually a consistent snapshot. That's it. Now, if you want to talk more about the technical details and everything, we'll hang around. My colleague Konstantinos is here as well. Please feel free to hit us with questions. Thank you.